Okay, why don't we go ahead and get started? Swapnil, are you ready?
Yeah, sure. So,
Okay. So welcome everyone. Thank you for joining us. We appreciate your time. Today's speaker is Swapnil, and he will be discussing transactions that work on replicated regions and how they scale for partitioned regions.
right, thanks, Marie. So, yep, we're gonna cover also the semantics of how transactions work in Geode as compared to, say, an RDBMS. See, how transactions work on replicated regions, partition regions, how transactions from client work. See, failure condition in all of the above three cases, and look at what is coming up. So in terms of semantics, the isolation level that Geode provides is repeatable read. What that means is when a thread in a transaction makes a change, only that thread is able to see that change until commit is called, and then so after commit completes, everybody else gets to see it. We have the implementation of transactions in Geode is optimistic, so we don't do all the locking up front, and instead our hope is that the transactions actually do succeed most of the time, and there is very little conflict um, in various transactions. So what we do is, instead of locking, we do conflict detection, and the readers are not blocked at any point. I'll come back to this conflict detection point later. So, and in terms of durability, as compared to an RDMS, we don't really have any transaction demarcation on the disk. But since Geode is a distributed data grid, it doesn't really matter. So as long as you have at least one member in your cluster up and running, your data will still be persisted, and it can be recovered from. So we'll also go into details about this later in the talk. So as far as the API is concerned, it's what you would expect a transaction manager to have essentially. So there are methods to begin and commit a transaction. So after you begin, you do all your region operations. You can do puts, creates, destroys, invalidates. So all the region operations essentially. And at the end, you either get to commit or roll back the transaction. One more thing you can do is you can also suspend transactions. So say you have made some changes in a transaction, and you want some non-transactional operations, say a region operation, right? So if you want to say create a region or destroy a region, then you get to, or you are able to suspend an existing transaction, do the other work, and then resume your transaction and begin. And so this kind of a workflow is particularly useful when you're using functions to execute a transaction. We'll also come to that uh, in a bit. So if you have single entry operations, then Gemfire region actually implements the concurrent hash map interface. So you have methods like put if absent, replace with passing in the old value and the new value, and the remove with passing in the expected value. So those three methods should be used if all you care about is consistency for one entry operation. And the transaction manager also has methods to add a transaction listener and a transaction writer. So a transaction listener is basically a piece of user code that gets invoked when a transaction completes. So it either could, commit or roll back. In either case, the transaction listener is invoked. And a transaction writer is again a piece of user code that gets invoked um, after Gemfire has done all its delocking and conflict checks, and just before the changes are applied to the cache. So this is the last point where user uh, could have a say in whether the transaction should complete or we should abort the transaction. Okay, now coming to the implementation. So in terms of implementation, so the isolation is implemented as a thread local. So thread local is a structure in Java which is guaranteed that is local to a particular thread. So no threads essentially see uh, one thread local variable. So that's what we use for implementing the transaction state. So whenever you make any entry operation in a transaction, that operation just ends up in the thread local. What we also do is then have a pointer to an existing entry in the region also be in that thread local. And so at commit time, when we say we do conflict checks, is there a question? Okay, I'm going to continue. So at commit time, when we do conflict checks, we check to see if the reference that we had stored in our TX state is still valid. As in, we do a get again and see if the world has changed underneath us, and if it has, then we throw a commit conflict exception. Also for the repeatable read case, right? So if a transaction does a read, then we copy the existing value from the region into the transaction state. And so for all subsequent reads for the same entry, we are able to then return the same value despite the world underneath us changing. Okay, so so this is a small sequence diagram on what happens at commit time. So at commit, when a transaction member says, so when you have essentially done a begin, a number of operations, and then you call commit, the transaction member gathers up all the keys that are involved in the transaction and sends a lock request to the D-lock grantor, which is one member in the distributed system. So the D-log grantor then says, yes, go ahead. I've locked those that set of keys for you, so that no other transaction will then be able to get to lock the same keys. Then we do the identity check, apply all the changes locally, and so at this point we build up one big message which contains all the operations in a transaction, and we send that message out to all the replicas. We do not wait for an ACK for that message. So after we have sent that huge message, we again send this apply commit message at this point to all the replicas. And so I'll come back to why we do that again. So after we've sent the apply commit message, all the replicas then apply that commit locally to their local caches, and and at that point we can go ahead and unlock our keys, and the transaction is then considered complete. So as I had mentioned that we actually copy over the values that are read in the transaction state. So that requires that we must have this copy on read property be set to true in Gemfire. The lock grantor is a single point of contention in the system. It actually is the eldest member in the system. So if that member crashes other members assume the responsibility of being a deal of grantor, and it is highly available, but it still is at all times a single member in a system, so it's a point of contention. Um, so what um, so when I said we don't do eager entry level locks, right, and instead rely on conflicts, the side effect of that is uh, at commit time, right? So when we are actually applying all the changes one at a time to the cache, some other thread may be able to see intermediate state. So consider that a transaction is changing, A to A prime and B to B prime. So it may have changed A to A prime, but before it could change B to B prime, another thread read both the values. So it essentially saw A prime and B, which is a problem. So in that case, so what we suggest is even the reader thread should do its read within a transaction. So and so when that thread then goes to commit itself, it will get a commit conflict exception saying that the world has changed underneath, and it actually did read a partial state, and that transaction will fail at commit. To enable that behavior, however, you will have to set this detect read conflicts property and set it to true. So one of the other problems, I guess, with detecting conflicts as references is transactions are prone to an ABA problem. So what that means is if the value was A, when we copied the reference, um, if then some other transaction changed the value to B, but then that the reference changed back to A when the first transaction came to commit the transaction. As far as the transaction is concerned, it still is the same reference, so nothing has changed, which is not true in this case. It's so even that is it won't happen, I guess, all the time, but it is could could potentially be a problem. Um, and so when I so on this slide, when I mentioned that we build up this one big message which has all the operations, so side effect of that is when you are doing all your transaction operations, we tend to bulk them up, right? And so instead of sending individual messages, we only end up sending one big message with all your region operations. So you end up getting better throughput when you're using transactions as opposed to when you're not. Okay, so let us consider some failure scenarios. So if a replica fails, then the transaction actually still goes ahead and commits, and there isn't really anything that needs to be done, because when that replica comes back up, it will do an initial image operation. So it will essentially get all the state from one of the existing members, and all the other members would have uh, the transaction state already applied to their local caches. So this member will get the transaction when it recovers, and everything is good. And so what would happen if the coordinator then fails? So when the coordinator fails, all the other replicas. So okay, let me come back to this. So what happens is when we send this one message which has all the operations, it also has a list of all the members who are part of the transaction, who are who also have the regions which are involved in this transaction and hence are in the transaction view. So all the replicas know who the other members are. So they are then able to gossip among themselves to arrive at a conclusion as to whether the transaction should commit or not. And so so what happens is, it depends on in where exactly the coordinator failed, right? So if the coordinator fails when it is sending so say the coordinator has sent the message to the first replica, but before it could send the message to the second replica, it crashes. In this case, none of the members or none of the replicas would have the apply commit message. So they would gossip, and none of them would have it, so they would decide to abort the transaction or not apply those transactional changes. If, however, the coordinator fails, after it sent out the first apply commit message, then the replicas would talk. They would see that at least one member has this apply commit message, which actually means that all the replicas got the the commit message containing all the entry operations. So they could at this point safely go ahead and apply the transaction, and everybody who was meant to get the transactional changes will get the transactional changes.
Hey, Swapnil, just one more question on a failure scenario.
Mhm.
Um, so if we're looking at that transaction coordinator, it's building up transaction state. Um, if if during that process, like before even a commit is sent in from the client to say I'm ready to go forward with this transaction, if that
Mhm.
TX coordinator goes down, that transaction will fail, right? So we don't actually replicate transaction state.
Before you
Not,
do a commit. Yeah, no. So in this case, I'm actually talking about when your application embeds Gemfire, right? So essentially, your application threads are running on a replicated member. So if then that member crashes, it means your application has crashed at that point. And so when it comes back, it will have to retry the entire transaction.
yeah, correct.
All right. Okay. So yeah, that was it for. So yeah, I should. Yeah. So these failure scenarios are all scenarios on what would happen after a commit is called, I
Swapnil.
guess. Yeah.
So there is a question here on the chat. I'm not sure if you're following that.
I am not.
Okay, I can read it up for you. That's fine.
Yes,
So the
please.
question is there a way to avoid the ABA problem, like an attribute set or something?
Um, well, hmm, the way to avoid this ABA problem at the application level actually might be that so you don't try to insert the same values, right? So say you did a get and you got a value, you changed it, and then you put the same object back in, right? And so if you keep on doing that, then that would be that is how get the old reference back into the same thing, right? So as long as you're doing um, cloning, right? So if you read a value, you clone it, you make a change, and then you put it back into the cache, you'd be able to avoid the ABA problem.
Okay. So Wes, I hope that answers your question. So now I also have one question, Swap, if you allow me.
Yeah.
Uh, the the non-transactional threads that may see intermediate state, can you expand a little bit on why that may happen, given that thread local isolation and that state would only
Yeah.
be, yeah.
Yeah, so sure. So this actually was at a level where the isolation level or the thread local applies until you have called commit. So you do a begin, right, and then you do all your entry operations. So those entry operations, at that point everything is isolated, so nobody is going to see any intermediate state. But when you call commit, at that time we do reference checks and delocks and everything, right? And then it is time to actually then take those changes and apply them to the cache. And since we don't have or don't want to have a higher level lock, which would prevent all which would essentially prevent the other threads from trying to operate on the cache, right, for doing reads. What ends up happening is we iterate over all the entries and apply those entries one by one to the cache.
Got it.
And so for that brief moment, right, at commit time, you could see partial transactions.
Awesome. Thank you.
Sure. Okay. All right. So let's see how transactions work on partitioned regions now. So pardon me for my PowerPoint skills. This is very rough, I guess. But then I hope it gets the idea across. So in this slide, I've tried to show 3 Gem5 members, which are hosting a partition region. And then your application, so even in this case, your application is embedding Gemfire as a cache and is actually running on one of the members, right? So in this case, then if your thread does an operation on a PR, right? Say it does a put, but uh, the primary bucket for that put is not local to that PR host. We then end up sending a message to the member who actually has the primary bucket. And so the transaction state then gets bootstrapped on that remote member. So at this point, if you then try to do another put, which say ends up going on a different member, right? So if the primary for that guy was a different member, then it ends up throwing this transaction data not collocated exception. So what that means essentially is that for partition regions, our transaction state is always where the primary exists for the first operation that you do in a transaction, and only one member has transaction state for a particular transaction. So when you do an operation, right, the first operation is what decides where the transaction is going to be bootstrapped, and all subsequent operations are then forwarded to that member, even operations for a replicated region that you may have in a transaction. And if you do an operation on as mentioned in the previous slide, we throw this transaction data not collocated exception. So the advantage now of doing this is our delock service is now striped on all the primary members. So you could have transactions on a set of keys, which are say belong to member 1, right? And a set of keys that belong to member 2. Then all those 2 transactions could go on in parallel, and they have absolutely no single point of contention in the system at all, which is nice, I guess. Right. So how do you actually ensure that you have this, or you target one member with your transaction. The way to do it is through data collocation. So um, uh, while designing transactions for partition region, we ended up referring to this Pat Hillen paper in called Life Beyond Distributed Transactions, which says that if you want your applications to scale, then they must the application should work on a collection of data, which he actually calls an entity. And he says that entity should always live together within a same JVM, essentially. Um, so uh, if you follow his advice, right, and you will be then able to scale your applications with Gemfire using either custom partitioning or data collocation, as depending upon whether you want your transactions. So custom partitioning is where within a one partition region you want to uh, specify how your data is to be distributed. So say you may have a trades region, and so you could then define a custom partition resolver that would uh, make sure that all trades for January are belong to one member, and then all trades in February belong to another member, and things like that. So that would allow you to then have your transaction on all trades in January in one of the transaction, and that transaction is then guaranteed to not throw a transaction data not collocated exception. If you did have two or more partition region, then you could also have a custom partition resolver. So a typical example tends to be a customer and all the orders. So you could have a partition resolver which would enforce that a customer's orders belong to the same VM. So in a transaction, then you could update a customer's orders. Okay, so on to failure scenarios for partition regions. So before a commit is called, if the TX host crashes, so we don't distribute the transaction state to the other members. So if the transaction host crashes, then we get this transaction data node has departed exception. If not the transaction host, then if some other member crashes, depending upon how you have set up your redundancy recovery, there might be a rebalance operation going on when a new member crashes or a new member joins your distributed system. So we actually wanted to give higher precedence to rebalance as compared to transactions. So if we ended up locking the bucket to a particular member, while transactions were taking place, we may have ended up starving rebalance, and we didn't want to do it. So instead, what happens is rebalance can continue when a transaction is occurring, um, but the transaction then ends up failing with a transaction data rebalanced exception. Let me point out that we still so this transaction data could only move between begin and when you call commit. At commit time, when commit is called, we go ahead and we grab all the primary bucket locks. So which means that no primary is then able to rebalance essentially or move to another member. And so while the commit has been applied, and that prevents a whole lot of problems, I guess, at that point. So so that was for before commit. So after commit, if the transaction host crashes, so one of the implementation details, I guess, is that a bucket region is underneath the hood, just a replicated region. So the semantics of failure that we had discussed for replicated regions apply uh, for bucket regions as well. And so it would be the exact same thing, right? With one caveat though. So what happens is in for partition region, the transaction state itself might be on a remote member. So while the remote member is executing a transaction, it would do the right thing. It would either commit the transaction so that all the members have the transaction state, or none of them do, right? So it is consistent, but uh, before your application thread hears back from that remote member could fail. So even though the system is consistent, you don't know what exactly happened in the system. So in this case, we throw this transaction in doubt exception. And the other failure, I guess, is when one of the replica crashes. As discussed earlier, it's still uh, the same semantics. So there's no problem. The transaction goes ahead and succeeds. Okay. So on to client-initiated transactions. So when a client does a begin and then tries to do all its operations, by default the client is talking to one of the servers. So it then ends up sending all the operations from after begin to one server, and then it only continues to talk to that one server at all times. That server, or delegate, I guess, on this slide may have the primary bucket for the transaction or may not. And so if he doesn't have it, then he ends up forwarding that request to the actual primary member. So this continues. So if, say, in this model, the delegate fails, then the client ends up talking to another server, and that server then ends up sending a message to all the members saying, hey guys, does anybody have a transaction for this client going on? And so the transaction host is then going to answer that, yes, I have this transaction. And so the transaction then continues from the client. And all this messaging is completely transparent to your application. So all that communication is handled by the Gemfire client. One more thing here is when the client then calls commit, at that point all the operations which are in the on the TX host are sent back to the client and then applied locally to the client if the client has caching proxy defined as its region. Okay, so let's discuss a little bit on how transactions interact with other Gemfire features. So, well, for, for eviction and expiration, it actually would be a problem if, say, you had eviction or expiration for that matter on a region, and so you are doing your transaction, and that entry then expires at when you call a commit, you get this commit conflict exception because the entry expired. There's nothing you could have done, right? So what we do is if an entry is involved in a transaction, it is reference counted essentially. So we increment a count on the region entry, and if that count is greater than 0, then we prevent eviction and expiration action for that region entry, so that you don't get a commit conflict exception. For OQL, so we discussed that Gemfire has repeatable read semantics, but that read turns out to be only gets that you do, or get operations on the region. OQL doesn't really honor the transaction state, so it still continues to read only the committed data at this point. Persistence. So by default, transactions on persistent regions are not allowed, and the reason being, we don't really have transaction demarcation boundaries on the disk. We do have this system property though, which allows you to turn on transactions for persistent regions. And so, well, the argument for not allowing transactions is, say you have a data center, right? And then you're doing all these transactions. So transactions are bound to succeed as long as even one member is up. So if consider all the previous failure scenarios that we had discussed, right? So if a transaction succeeds, then by definition, when the other members, when they come up, they are going to do an initial image operation, or get the initial image from the member that is already up, and they get the current state, and everything is happy. So as long as you have at least one member that survives, we don't really need transaction demarcation on disk. So but then just to prevent from the very corner case that all the members in a data center die at the exact same moment and you had persistence, we have not allowed transactions on persistent regions by default. And functions, yes. So well, one of the workflow that we've seen many people implement is they use functions to invoke transactions. So in a transaction, in a function, you may then do a begin transaction, do your operations, and before the function returns, you suspend the transaction. So at this point, and potentially send back the transaction ID back to the client, so that on subsequent requests, you are then able to send that transaction ID and then resume that transaction. So this would enable you to have one client execute multiple transactions at the same time, or even have multiple clients participate in a single transaction. So we have seen most of these, or not most, all of these exceptions, I guess, which could be thrown by the transaction machinery. So all these exceptions actually extend transaction exception, which is and so our advice to people, if you want to use transactions, then implement your transaction within a loop and always catch this transaction exception and retry your transactions, and that would handle most of these situations. Because so say for commit conflict, state underneath may have changed, so you want to retry transaction data node and data not collocated. Well, so all these exceptions are prime targets, I guess, for retrying. And when if you just retry, the transaction would then succeed.
Swapnil,
Yeah.
another question here on the chat from Ashvin. So what are the challenges in persisting transactions marker on this?
Well, we just haven't gotten to it. um, we actually do have well, several specifications which outline, how we would tackle this problem. But given that there the only case where we actually need this is is when all the members in the system have crashed at the exact same moment. That somehow, well, it's treated as it actually is a very, very corner case, right? So handling of that corner case has never become a priority, I guess, and that's why we don't have persistent or transaction demarcation on disk.
Hey, Swapnil, on that point where all the servers in the grid crash at the same time and you have transactions turned on and persistence equals true, is it that there's a problem with the cluster coming back up if the transaction was in process? Or on the other hand, is it that you just can't guarantee the end state of the transaction?
It's just that we can't guarantee the end state. So we may have only persisted. So if your transaction had, say, 10 operations, right? We may have only persisted 5, and then the server dies, right? Or the entire grid dies. So when you restart the grid, we will only recover those 5 operations, and essentially lost half of the transaction. So that's the problem. That's the only problem, I guess. All right. So any other questions? All right. Let's continue. All right. For JTA, so the so frequently you actually need to make sure that Gemfire works with other data sources that you have in your application, and then to coordinate transactions amongst these data sources, JTA is the default, or okay, is the industry standard. So Geode enlists as a synchronization with an external GTA transaction manager that may have Bootstrap. So you may have Geode embedded in a WebLogic server or a WebSphere server, or any of the application servers. They have their own transaction manager or GTA transaction manager implemented. So Geode just registers as a synchronization in order to get notifications for prepare and commit. So Geode is essentially a last resource in that in that transaction. So it is last to prepare but first to commit, and so the outcome of the transaction depends on what Geode decides. The transact if Geode succeeds, then the JTA transaction succeeds. If Geode fails, then all the other data sources who had prepared the transaction then roll back the transaction. We also have a JCA adapter, which is used, which is required for this last resource commit optimization with the WebLogic server. Geode itself ships with an implementation of a JTA transaction manager, but that transaction manager is not persistent, so it's not really recommended for production use. And all right, on to what is coming up next. We have an issue Geode 16, which talks about getting rid of the co-location requirement that we have on the partition regions currently, and potentially, supporting distributed transactions. Although there aren't really any issues filed on the Jira for these, but some of the things that have been requested several times are that Gemfire be a complete XA data source, that we implement persistent transactions in order to get rid of the system property workaround, and that our query engine actually reads from the transaction state.
Hey, Swapnil, one question on this roadmap. Have we ever had any requests to fail over like in-process transactions so that we have better high availability on transactions?
Not that I'm aware of. So our recommendation has always been to wrap the transactions within a loop, right? And retry it, catching commit or catching transaction exceptions. So with that, I haven't come across any requests for high availability of transaction state. Because even that is just pre-commit, right? So if you haven't even committed, then the application is then able to just catch the exception and then retry it on some other member.
Okay, thanks.
That was it, actually. Unfortunately, I don't have a questions slide at the end, but just wondering, anybody have any more questions?
If you have a question, just put it in the chat. We have one from Ashvin. What are the challenges in persisting transaction markers on disk?
Yeah, I believe I already
Oh, sorry,
replied.
did you already answer that one?
Yep.
Anyone else? Okay, if there's no other questions for Swapnil, is there anything that anybody would like to bring up or anything they'd like to share if they went to ApacheCon? No? Okay. In that case, thank you very much for your time, Swapnil, in presenting. This session has been recorded, and I will post the information to access the recording on the dev and user list. Thank you all for attending, and I will see you at the next Clubhouse.
Thanks, guys.
Thank you.